Okay, so last week we stated this proposition without proof. So I will start by proving this proposition, but before that, let me recall a bit what we did, because we will need lemma 2.16 in this proposition. So what was this lemma? In fact, yeah, it was something about the Frobenius-Shaw indicator. So the Frobenius-Shaw indicator is defined by this picture in general, and its trace, this scalar. So we show that it is the nth root of unity here, and here. So we consider this picture where kappa is some morphism between x and x dual. X is an object, etc. So here, in fact, you can move the kappa on the other way and remove the pivotal structure up to multiplying by the Frobenius-Shaw indicator. So this is this lemma. So we will apply this lemma to prove this proposition now. So let me read again the proposition. So you consider a pivotal fusion category, A is a pivotal structure. You take a simple object. So note that we need fusion category here. In the section, we consider the only monoidal category most of the time. But here, the proposition requires the category to be fusion. So X to be a simple object. In the previous lemma, we did not assume X to be simple. Self-dual. Then its pivotal structure, isomorphism, is just the identity times the pivotal, the second Frobenius-Shaw indicator. So in particular, if you consider the composition of the pivotal structure with itself, so it's a natural isomorphism between the identity functor and the force dual functor, then you consider this constant square, but it's a 2 root of unity, so it should be 1. So for this square of the pivotal structure, every this isomorphism for on any simple object is the identity. Okay, so proof. So we need to apply the previous lemma with kappa equal identity of X. And here we will, it may be more convenient to write algebraically and not pictorially. So, so X, not that. So what should I write? Okay. So X star equal X. This is okay. This is by assumption. By assumption. By assumption. Now, so we can apply the this algebraic, this formula to kappa equal identity, and we don't need to care about star everywhere. So then so Fx compose pivotal structure tensor identity equal Frobenius indicator X. Fx compose identity tensor identity. Okay, but so the pivotal structure is an isomorphism between X and itself. So X and X double star, but we know that X star equal X. So it's an isomorphism between X and itself. But X is simple. So this home space is one-dimensional by Schur lemma. So by Schur's lemma, this space is one-dimensional, and so it's an isomorphism. So it's a constant, but non-zero constant. Ax equal kx identity of x with kx a scalar. So identity is an element of this space, and this space is one-dimensional. So every element is a multiplicative constant of the identity. So so what? Okay. So you consider here, you replace Ax by kx identity. So you have identity here with some multiplicative constant. So you compose with identity. So you can forget about that and just consider the multiplicative constant. This is what kx fx equal show indicator fx. But fx is different from 0. So kx equal the second Frobenius indicator directly. And we have that Ax is like that, which is what we wanted to prove. That is the first. And then now so like that. You have to be careful. Is Ax double star composed with Ax, but Ax equal Ax star equal X double star. So it's like that. So yeah, it's obvious. X star equal X equal X double star. Okay. Oh, yeah. Write it like that. X double star equal X star equal X. So this is equal to the the second condition indicator, which is 1 by the proposition 215. So it's a root of unity, n root of unity, 2 root of unity. Proposition 215. Okay. So we proved that in this specific case, the pivotal structure isomorphism on a simple object is just given by the second formation indicator and the square of the pivotal structure is identity on the simple object. Okay. Okay. So now we can start section 3. Preliminaries on fusion category. So the last statement was about fusion category, but it was, in fact, consequences of all the preparation in this section 2. So I put it in section 2, but section 3 will be all specific to fusion category. Okay. Some frames to be fusion about bilinear form. Attends, j'ai notre truc allumé. Allô, allô. Tu m'entends pas du tout ou tu m'entends pas bien? C'est bon? Okay. So sorry, the sound was not working well. So now it should be okay. So let me write the sentence I just said. So this section proves some preliminary result. Requiring the monoidal category to be fusion. Fusion about, so some result about some linear form. And the resolution of identity. Okay, so a small remark about convention about the identity. The unit, about the unit object. So the usual convention, so in a fusion category, the unit object is simple. So the morphism between the unit object and itself is one-dimensional. So this endomorphism between one and itself will be sometimes identified with the field itself. Okay, and okay. Any object isomorphic to the unit will be identified with the unit. Okay. So some usual convention. So let's see the fusion category. Recall that MC1 equal is one-dimensional generated by the identity. So the morphism KID1 will sometimes be identified with the scalar K itself. Moreover, any object isomorphic to the unit will be identified with the unit. Any object isomorphic to one will be identified with one. Which means x isomorphic to 1 implies x equal 1 here. In particular, one star equals. Okay. Now, so let me explain what kind of bilinear form we will consider in this section. In this lemma. So let's see. Be a fusion category. You consider an object, and we will consider a bilinear form involving two morphisms between one and the object Z, or one in the object Z star and the evaluation of Z. So let Z be a fusion category. Let Z be an object in C. Consider a bilinear form so I will write a picture of it. Let me write where alpha and beta are not being lost with the notation. So alpha is a morphism between 1 and Z star, and beta is a morphism between 1 and Z. So you have two such morphisms. So I wrote this short notation. I just write it as a couple with the direct product, but it does not just mean that one is here and the other is here. So we will define a bilinear form involving alpha and beta like that, as follows. So evaluation of Z composed with alpha tensor beta, which can be depicted as follows. Z star. Okay, so remember that the one is omitted by convention. also. So what about this bilinear form? So then we will talk about basis, a kind of orthonormal basis. We'll state the existence of a kind of orthonormal basis according to this bilinear form. Then there are basis EI, big I, capital I is a set of indices. So prime here. The basis of home C1 this star. So two bases in fact. We need a plural basis. So another basis for the other space of home C1. So we put the same index set because these have the same dimension. Dimension of that is just the number of unit components here, which is the same that here. So we have two bases, okay, such that B I prime E I prime I J equal Kronecker delta of ING. Okay. And that okay, it is the first step of the lemma. And for all alpha beta in space, yeah, so alpha and beta decompose using this basis. So alpha equal sum I of in I involving the bilinear form. EI prime I P EI beta EI, and I made a mistake somewhere. Let me check because there may be, we may need to have a prime somewhere. Let me check. So what is it? 3, 2. Wait a minute. So I did not put prime. So should we put prime somewhere here? So beta is there. Prime is basis for that. So you should not have prime here. And here, alpha, this one, alpha correspond to that, EI, so that corresponds to that. Wait. So where I forgot something. So this one corresponds to that and that. Okay. So this one is here. So here, I guess. So if I'm not mistaken, we should put a prime here. So it's the details, but prime. Let me write a prime. Anyway, we will see in the proof if we should put a prime here. Let me check the proof. Yeah, I guess there is a prime. Alpha bit. I forgot the prime everywhere. Anyway, so tac. Okay. And so we have that, and so B alpha beta is sum alpha EI B de I prime beta. Okay. Okay. So in particular, you can say that this bilinear form is non-degenerate. In particular. Linear form is non-degenerate. Okay. So let me see here. Okay. So proof. Okay. So it's, yeah. It looks complicated, but in fact, this is completely straightforward. There is you don't need any ID to prove that. It's just you just need to write the proof. So first, C is semi-simple because it's fusion. So the object Z can be written as a direct sum of simple objects. We'll see. ZG, simple object. Okay. But the category is additive. So the morphism also can be decomposed according to the decomposition of Z. Alpha can be decomposed, beta can be decomposed, and also the evaluation map can be decomposed. Let me put a bit more space here to be more readable. Where is it? Okay. E, Z, one direction. So where alpha G and beta G are, as you can expect, where alpha G, beta G are in space 1 dg star times 1 dg. Okay. So that's immediate by additivity and semi-simplicity. Then beta, and by linearity, beta alpha b de alpha beta is just the sum for like that. Evaluation z g compose alpha g tensor beta g. Okay, so we are just we are just decomposing. Right, we are just writing this as the direct sum of something like that. The direct sum. Okay. So remember that all the ZG are simple. Whoa. So if so here, if you decompose this one and this one, so this is a direct sum, this is a direct sum. So you pick a component here, you pick a component here. If it is not this, if it is Z E star ZG with E different from G, then by Schur lemma, this will be 0. Okay, so you can take the same G. Okay, that's why you directly get the sum. There is no you don't have a sum over EG. You don't have a sum over EG because when E is different from G, you get everything 0. Okay, so that's okay. Then, we will, so this so wait, what am I writing? Okay, so here it's a beta for alpha. It's a formula for alpha beta. But what about the formula for this B of that? B of that does not make sense because this is not a good space. But you can produce, we will make some alpha G tilde beta G tilde, where living in the space, this space, as follow, and then we will be able to apply beta on the tilde. So let me explain. So B of alpha E tilde alpha beta G tilde equal. So let me write what is the definition of alpha beta before writing what this is equal to. So we alpha beta in the big space, both such that, or with alpha. So if you consider the is component of alpha G tilde, it is 0 except if G equal E. So it's like you put 0 everywhere, except you put 0 in every component except for the component G. And same for beta. So that in that way, you get a model of beta, but in the big Hom space. This completely define what is the T, beta T. So you get, so what this is equal to delta, Kronecker delta EG, evaluation map of G composed with alpha G tensor beta G. Okay. 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 So now, so we get that. Now, the goal is to make some basis with orthogonal relation. So we are almost. So let me see. Okay, so now, remember this Hom space. In fact, if this component is not the unit object, then this Hom space is equal to 0 by Schur lemma because it is a simple component. So you only need to care about the indices for which the component is equal to 1. Otherwise, it's 0. But if G is different from the unit object, then by Schur's lemma, and here we use the here we need the convention that every object isomorphic to the unit is identified to the unit. That's why you can write different form. Otherwise, you will need to say not isomorphic to. But we don't need to care about that. So then, by Schur's lemma, the Hom space so let me write it here. Hom space. So as usual, is equal to 0 is equal to the Hom space 1G star. And in this case, alpha G, alpha E, alpha G equal beta G equal 0. Okay. So we only need to care indices for which the component is not 1. Is 1. So only need to care indices for which the component is 1. So let be this set of indices such that the component is 1. Let consider an indices in I and let okay, so what about now? Okay. So consider E. So these two elements, which will each of them will make. So we will use them to make the basis. So they are taken in this big Hom space. Such that, as for the tilde before, E prime G equal equal delta EG, identity of 1. Here we can they are the same. Here they are separated here, but here you have the component is 1. So the dual of 1 is 1. So they are the same. Okay. Okay, so what about now? Now, we have what? So what about this? Let me check. Okay. So now we will consider this formula. So we can apply this formula to here, because in fact this couple is exactly of this form. So we will consider this part. So now, okay, now this part equal 1. So this is this part. So this part is just 1. So so let me write. So I don't understand. So beta. Equal delta G equal delta G. Okay, because this is nothing but 1. This is equal to 1. Okay, and that's true for all ig. So it looks a bit confusing, but it's only just technical. In fact, there is nothing complicated here. Okay. Now, so note that the cardinal of the index set is just the dimension of the home space. Because it is exactly the number of components equal to the unit object. Okay. So, okay. So you have this kind of so is it here? Orthogonal relation. But the number of objects is exactly the dimension. So it's a basis. Okay. So by bilinearity, E prime I is a basis of this one. and EI is the basis of this. Okay. So we will finish the proof after the pause. So, and after the pause. The pause. Okay, so we made basis. Now, what remain to prove? So we proved the first part up to here. Now, what about the rest? This one is really okay. So what about the rest? So we need to consider alpha beta in general. So any alpha beta can be decomposed using the basis. All alpha beta in C1 is C1Z alpha equal sum for I in I alpha E1 that and beta equal sum I this is okay. By linearity, in fact, and we just apply this equality, the fact that they are basis. Okay. So B of alpha beta is exactly the sum for I and I beta alpha EI beta EI prime B. So yeah, I said beta for B. B of alpha EI, B of EI prime beta. Okay, because by bilinearity, again, you again apply, in fact, this formula. Replace that by that here, etc., etc. So it's completely clear. Okay, so now let me warn you a bit about the notion of dual basis, because in fact, EI prime can be considered as a dual basis of EI, of the EIs, according to the bilinear form, and dual in the sense of vector space. But they are not dual in the sense of category. EI prime is not EI star. You have to be careful. In previous lemma, EI prime, so this basis is a dual basis of this one according to the bilinear form B, where dual is in the sense of vector space. In particular, EI prime is not EI star, the categorical dual of the morphism EI. EI. Okay. Okay. So another kind of remark, but I wrote it as a lemma. You have to be careful. In fact, this lemma will be about, okay, so when, so let me state here. Yeah, so it's really long. So, in fact, this basis depend, so this, so this depend on Z and Z star. So you have one basis for Z star here, one basis for Z here. But so you have Z and Z star. Now, if you replace Z by some X, so how to say? If you replace Z by X star, you will get a basis for X double star, X star, which this one is like X. X double star is isomorphic to X in this case. So you will get a basis. So in particular, if you take, I don't know, if you take Z star here, you will get Z double star, Z star. So you will get a basis for Z star. But you already have a basis for Z star with Z. So there are two ways to get a basis for Z star. By starting by Z or by starting with Z star. And to avoid any confusion, in fact, about these two bases, this lemma will say that these two bases are the same in some sense. So let's see the fusion category. For any object Z in C, so I denote the bilinear form with an index Z to avoid any confusion, because we will consider several different Z. B, the bilinear form. Mentioned in the previous lemma, and also the basis like that. EIZ, I in IZ, be the basis of home 1Z. So mentioned in the previous lemma. So we fixed an object Z and we put some indices to avoid confusion, because we will consider different possible Z. For all objects X in C, and for all ij we have, so Bx we'll consider z equal x and z equal x star. Zx ei x star ijx equal bx star ei x double star ij x star. So you see, so let me check here. Z equal x, and so the first involve x star and the second involve x. Here z equals z star, so you have x double star x. That's okay. 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 This is what I wanted to say. Where? Okay. So the index set, these three index sets are identified. So this is equal to delta ij. So what do you see? You see here, you have these two are in the same, are the basis of the same space. Okay. So here there is a subtlety. By definition in the lemma, this is the basis of that. From the lemma. So in the lemma, we have a basis for that and a basis for that with a star. We don't consider the basis with a star. We only consider the basis for this one. And for the star, if you want to put a star, you put a star, but it's, yeah. What we are saying here is that this is you get the same result. So that it's a, yeah. It's okay, just a details. It's just a details. You have to be careful, but it's not very fundamental. Proof. So in fact, this is completely trivial because when you look into the details, when you look into how these things are defined, in fact, there is no confusion possible. But when you make a definition of something of this basis and then you use this basis later and you forget how it is defined, this can be confusing. That's why I wrote this lemma. But in fact, in details, this is completely trivial. So in the proof of lemma 3.2, the chosen basis EIX star I in X star does not depend on whether Z equal X or X star. Does not depend. As I said, there are two ways to get this space, but the way the basis is defined does not depend on one of the two ways. On whether Z equal X or X star. So it's a small details, but Okay, so that's okay. So what about now? Now, so in the next lemma, we will come back with some picture. So we will consider the home space between 1 and z star. Z will be here x tensor y for two objects, and we will prove something involving the traces. So let's see the pivotal fusion category. With pivotal structure A. Okay. Let x, y be two objects of C. In C. And Z here will be x tensor y. So we will consider two K-linear maps. The K-linear maps, following two K-linear maps. So F from the home space 1 z star to the home space x y star, defined by the following picture: f of alpha equal, so I will only define it by a picture like that. Okay. So you have alpha. Alpha is this, so where is alpha? Okay, alpha is in this space between 1 and y star x star. And then the map is just to do like that on the second leg. So it looks like a bit what we did with formulation indicator. You deform a little bit this picture like that. So we get a map from Z to X star, from X to Y star. So I'm sorry, I am a bit confusing today because I did not sleep enough last night. I'm a bit tired, but it should be okay. So the second K-linear map from 1z to O C y star x defined with this picture. A little bit more complicated, but in a allô, allô? Non? C'est bon? So you are making the dual. And here, then, only this one continue. Do inverse of pivotal structure. X, Y star. Okay. So it's okay. It's this picture define, well-defined the linear map between this space and this space. So, what about these two linear map, K-linear map? In fact, if you apply the trace to the composition of these two linear maps to alpha and beta, you recover the bilinear map of before. Then trace of f of alpha compose g of beta equal trace g beta compose f of alpha equal the bilinear map B defined before of alpha beta with B from the bilinear map, the bilinear map from lemma 3 point. Okay. So you see that this will be not difficult to prove. In fact, this will only involve, so you will make the picture. This will only involve the definition of a trace, some lemma 2.5 when you move some pivotal structure from the left to right, and the definition of pivotality, and you can say the proof is straightforward, but let me write it in details. So trace of f alpha composed with g beta is, by definition of the trace, definition of trace. So let me write first f of alpha composed with g beta. So g beta, so beta, like that. Then you move, so what is beta? Okay. You move one, so which one? This one. Here, and you have A inverse of x. So this is beta. And no, this is g beta, sorry, g of beta. Then you compose with f of alpha. So you put f of alpha here. So in fact, this curve should be straight. Okay, like that. So this is alpha, okay. And then you apply the trace. So remember the definition of the trace. So our definition of the trace involves an extra pivotal structure and that. Okay, so this is okay. Just the definition of the composition and the trace. Then you apply the lemma 2.5. Remember, this is a lemma with which you can move a pivotal structure from left to right. We will move which one? This one here. Here, in fact, left to right, but you can put it here, it's okay. And so you can remove that, and here we will put something like that. Yeah. So beta. That. A inverse x, A inverse y. Okay, alpha here, here. Okay. Then here, what you have beta, the categorical dual of beta, and double dual. And then you apply the pivotal structure. So in fact, remember by pivotality, this is exactly beta, by definition of pivotality, which is equal to B. So pivotality. So I write directly with Z instead of X and Y. It's shorter. Okay. So you have just that. So you have alpha, and you replace this big part by just beta. Which is the bilinear form applied to alpha beta as defined before. Okay. So yeah, I want just to put only one string because I wrote Z. So Z star. So by pivotality, you have that, and also maybe you can write X tensor Y equal AX tensor AY. That's why it's the same for the inverse. That's why you can replace this one by A the inverse. So that's okay. Okay, and this is exactly, as I said, the B of alpha beta. Okay. So we prove that. Is there something else to prove? Ah, yeah, we prove only the first. So we prove the first equality. This equal that. Now we will prove this equal that. So the proof, in fact, is similar. In fact, you will see the proof in this second case will be a bit easier. So next. Trace E beta compose F of alpha equal. So definition of the trace. So alpha. So let me write first alpha. Alpha is like that. Beta is like that. So E like that, and then you compose, and then you make the trace. So remember that we need to add this extra. Here we choose to make the trace on the right. Here, yeah, in both cases, we make the trace on the right. Okay, no, it's okay. Okay, here it is y star. That's why you have this extra y star. Here it is x, so you have just x. No problem. So that's okay. But see now that can be simplified directly here. So just by simplification, this is alpha beta. Okay. So the picture is less and less readable. Wow. Just want to clean a bit here. Okay, and now, so definition of trace, simplification. So, okay. Now you apply some zigzag relation. You have one zigzag relation here, and then one here. That's two zigzag relation. So you can, in fact, get directly that. So it is equal to by zigzag 2 times zigzag relation alpha beta. So you have that and that, which is exactly beta b of alpha beta. So you see this one is a bit easier because everything's this simplify automatically and then just two zigzag relation and you get what you expected. Or here we needed to move on the right and to apply the pivotal structure. So this side was a bit, the complexity was not symmetric between the two cases. Okay, so let me check the time. It remains 11 minutes. Okay, so so now we will state a result, state and prove a result about basis and this map F and G. To get, in fact, to get basis, so we will consider the basis we made for that and that. We will consider F and G, and then we will get basis for that and that. Because F and G are bijection linear map. They are bijection because you just need to do that, or here, or here, you just need to do that and that. And you can come back. So they are bijection, trivially bijection. Okay. So let me state lemma. We follow the notation of the previous lemma. Consider the basis EI prime I of OM1 Z star and EI of OM C1 Z okay, from from the lemma 3.2. So where these bases are written, prove to exist. Okay, so now we will consider so we will map this basis to the other home space involving X and Y with F and G. So let epsilon prime I to be F of E prime I and epsilon I to be G of EI. Okay, then the trace of epsilon prime I composed epsilon J equal the trace epsilon J composed. So you will see the proof is immediate, more or less, because it's just a reformulation of what we said before in the just a reformulation of what we said before. Then this is so this is the basis of home C X Y star, and this is the basis of home C Y star X. Okay. So the proof is immediate by what we said before. Immediate from lemma 3.2. So where do the bases are EI prime I are proved to exist, and 3.5 where you have this trace. So you have this trace. You have that, and by 3.2, when you apply that to alpha beta equal EI prime, it's a Kronecker data. So when you combine the two, you get exactly that. But you need also yeah, and maybe we don't need it. And the fact that F and G are bijective. Linear map. If you want to use the same argument of cardinality of the cardinality of the basis equal to the dimension of the space, you know the cardinality here is so this cardinality of that. So that is the dimension of this space. No, it is a dimension of this spaces, and so we need to be the dimension of this space. So there are the good dimension because it's bijective, as we said. You have something, and you can come back. So it's a bijection. So they are the same dimension. So it's okay. Okay. I'm sorry, today there is not too much picture today. It's mostly technical, abstract nonsense theorem, in fact. So it's not very interesting. But we need that for the rest, for the future. So let me state another technical lemma. But in fact, this technical lemma only involve algebra. It's not even in category. So lemma. We will use this purely algebra lemma. So let me state it and we will prove it tomorrow. So let A be a K algebra. Let O be a finite set. Let so Ix, no, not like that. And for all x in the set O, let I index x be a finite set. So, yeah, a K-algebra, one finite set and a family of finite set indexed by the first finite set. Let to xij x in O ij in ix be non-zero element of the algebra such that to x I j to x prime kl, so the product of two generic elements defined before is like that. Delta x prime delta j k dx, some constant, which will correspond to Frobenius indicator for the application of this lemma, like that, with dx in non-zero scalar. Okay. So I have no time to finish to state, but let me just read. So then I will read. I read what the end of the statement, but I will write it tomorrow because it will take a few minutes. I don't want to excess too much. So then the element, this element are linearly independent. So using this relation, you can prove that these elements are linearly independent and they generate a K subalgebra of A. So these elements are in A, and this generate a K subalgebra, which is isomorphic to a direct sum of matrix algebra M nx of K, with nx is a cardinal of that. So this generates a direct sum of matrix algebra. Okay, so we will finish to state that and prove that tomorrow. So end of session. So we will end of session. We will finish. Okay. So okay. On peut arrêter la vidéo.